Let's write a program now that has a function that, when given the coefficients to a quadratic polynomial, finds the roots of that polynomial. So what we're saying here is that given a polynomial of this form, ax squared plus bx plus c, we find the roots of this, which, remember, those are the values of x, such that if we set this equal to 0, that's what we get. And we're going to assume that a, b, and c are real. We won't have any imaginary parts for any of these to deal with. So we can use the quadratic formula for this. Which says that the roots are equal to minus b plus or minus square root of b squared minus 4ac over 2a. And because of this plus minus in here, this really represents two roots. So we'll end up finding x1 is equal to minus b plus square root of b squared minus 4ac over 2a. And x2 is equal to minus b minus square root of b squared minus 4ac over 2a. So before we start writing code, I want to sort of plan out what my logic should be. And to help me better understand it, I want to work a couple examples by hand. You can always sit down and start typing, and that's the mistake many people make. And if you know exactly what you need to do, of course, it's not a mistake. Think about if you have to drive somewhere. When you need to go to a store you've been to many times, you don't sit down with a map and figure out where you're going. And if you need to go to a store that's pretty close to where you've been before, you probably don't sit down with a map and plan it out because you already know how to get there. But if you don't know how to get someplace, some planning can save you a lot of trouble. So let's work a couple examples by hand and see what kind of observations we can make. So let's solve this problem. X squared minus 11x plus 24. And there's an implied 1 here. So this would be my A, this is my B, this is my C. So according to these formulas, we would get then that x1 is equal to minus 11, because negative 11 is the B, so we need to negate that, plus square root of minus 11 squared, sorry, this should be C in here, minus 4 times 1 times 24, divided by 2 times 1, which is equal to 11 plus square root of this would be 121 minus 96 over 2, which is 11 plus square root of 25 over 2, which is equal to 11 plus 5 over 2, 16 over 2 equals 8, which is one of the roots of this equation right here. And then the difference between the two forms is just whether I'm adding or subtracting the square root part. So that means that x2 is equal to 11 minus square root of 25 divided by 2, which is 11 minus 5 over 2, which equals 6 over 2, which is 3. So that's the other root. So the roots here are 8 and 3. All right? So when I look at this, try to make some observations, I had, since a, b, and c are real, I know that minus b over 2a has to be real. And in this case, the square root of b squared minus 4ac was also real, right? It was 5. And the reason for that was that b squared minus 4ac was greater than or equal to 0. That's going to turn out to be important. Let's do another example. So in this one, let's have 2x squared plus 3x plus 4. So that's A, that's B, that's C. So we get x1 is equal to minus 3 plus square root of 3 squared minus 4 times 2 times 4 divided by 2 times 2, which would be equal to minus 3 plus square root of 9 minus 4 times 2 is 8 times 4 is 32 over 4, because that's what this is, which is equal to minus 3/4 plus square root of minus 23 divided by 4. And I'm separating these out because I already see where this is heading, which is I'm going to have to find square root of negative 23, which means I'm going to have an imaginary number. And so this is equal to minus 3/4 plus I, or j, if that's what you're used to, square root of 23 over 4. Which means now that x2 is equal to minus 3/4 minus I square root of 23 over 4. So there's a root, and they're both complex numbers. They both have, in this case, a real part and an imaginary part. So in this case, what happened was b squared minus 4ac was less than 0. So when this happens, then I'm going to have an imaginary part that I need to deal with when I'm writing the results. And if b had been 0, then this would have been 0, there would have been no real part. But in many cases, I would have a real part plus an imaginary part here. So this is going to be a complex number. It turns out that in the C89, we don't have a complex number type, so I'll need to deal with this myself. Some later versions incorporate that, but not in C89. So we'll need to deal with that. So I think basically our logic comes down to figuring out what this relationship is, and then either producing only a real number or a number that has an imaginary part. So let's write the logic to do that. So if you can hear me, I know I'm going to have a square root, so I'm going to go ahead and include the math library. Put a little logic in here. Or I'll put the logic below, but this would be the form of our function. So we'll have roots given a, b, and c for y is equal to ax squared plus bx plus c. So I would normally include something like this to make it clear which parts are what. Because depending on your programming language or how you choose to approach it, you may choose to write things in order of the constant to b to a and so forth. All right? Roots, say we had 1 minus 11, 24 was one of our examples. We'll do that first because we know it only has real parts. And so what does my function look like? Well, I'm not going to return anything, so I'm going to have return type of void. And then what types should these be? Well, I happen to choose integers, but we don't necessarily need to be restricted to that. So let's say double A, double B, double C. And we'll have the function not only determine the roots, but also print the roots. So that's why I'm not going to return anything. So take this right here. And let's put a little logic in here. So if, we'll call it g equals b squared, or let's separate this out actually. If g is less than 0, we have an imaginary part that we need to deal with. All right, and then remind ourselves of the quadratic equation. or formula, excuse me. So we'll have x1 is equal minus b. And let's go ahead and write it like this. Divided by 2a, because actually I'm going to write at least parts of it like this. Plus, and if that's our g, then we have square root of g divided by 2a. And then we see the x2 is equal to that. All right, so it's just a different way of writing the quadratic formula where I separate out the parts, which makes it more suitable for when we get a complex number or something with an imaginary part. All right. So we need some variables. So double G, certainly to calculate that. G is equal to, we pass in A, B, and C, so it's going to be B times B minus 4 times A times C. And when we have that G is negative, then I'm going to have both a real part I need to calculate as well as an imaginary part. So I want some separate variables for that. So I'm going to put in here double x1 real, x2 real, x1 imaginary, x2 imaginary. And we probably want to do some printing in here as well. So printf oops. We'll say 0.1f x squared plus percent 0.1f, since these are all doubles, x plus percent 0.1f, new line. And so now we say if g is greater than or equal to 0, we know we don't have an imaginary part. So we'll have an if else. So if this is the case, let's calculate some stuff. So x1 real is equal to, we said minus b divided by 2 times a plus square root of g, which is already been calculated, divided by 2 times a. x2 real is just this with this part changed to negative. And let's go ahead and print the answer. So we get x1 is equal to percent 0.1f and x2 should be this right here. So we can fill this in a moment. This is legal. Well, let's check this since we know the answer to this is going to be integers. So since I'm using square root, I need to make sure I link in the math library if using GCC. And there's 8 and there's 3. So it says x squared minus 11x plus 24 has roots 8 and 3. Could we clean this up some and put the minus here and say minus 11? Sure, if I want to write a bunch of extra logic. But I'm not concerned with that right now because my focus is on the roots. To me, that's cosmetic, so I would typically do that at the end if I was interested in it. So now what do we need to do? Well, now we need to deal with the case where g is less than 0. So still have similar logic to this. But now we'll say, this right here. So we know this would be the real part. Sorry. All right, if we go back and look again, what we had, if there is a negative g, then this will be the imaginary part, or the magnitude of the imaginary part, and this will be the real part. So that's why I did the way I did it. Another thing to note here, technically I didn't need two different variables because I'm simply adding this magnitude or subtracting this magnitude, but they're the same magnitude. Technically, well, I guess these are the same. So I really had more variables than I need, but I wasn't thinking that far out. I could simply just, in this case, use the same values. All right. But we'll stick with this. So we need to clean this up. So this would be this. And g is negative, so I'm putting minus g in both of these to get the negative of a negative, which is a positive, because the magnitude is what I'm interested in. And then the way I'll make it look like a complex number is to incorporate that into the results. So plus I times percent 0.1f, or minus that. So we'll have x1 imaginary and x2 imaginary. So let's see what we have. Now I didn't put in something that should reach that, so I should still get the same results. But one of the nice things about functions is I can easily add in multiple things here. We're going to throw something in that has no real part. And we said this before was 2, 3, and 4. But as I was saying, the nice thing about this, it's easy to add this and just call a function, as opposed to taking all this logic and cutting and pasting it, possibly having to rename variables to accommodate these values if they were saved in variables. That'd be a lot of hassle. So hopefully you're seeing the benefits of writing your code using functions. So I rounded these off. So if we actually change the precision, and once again, here's something I can easily do. Let's make these 3 decimal places. We knew it was supposed to be 0.75 or negative 0.75 actually, which got rounded up to 0.8. And there it is. And these are correct. I checked these with a calculator earlier. So these should be fine. So there's our 8, there's our 3. Here's something with no real part down here, which once again, if we want to put the logic in here to detect b being 0, we could deal with that. And then this is a complex number. So I've sort of created my own complex number here in terms of how I display the results, but it has a real magnitude and an imaginary magnitude. So there's another example of using functions that hopefully demonstrates the benefits of putting your code into functions and then just calling it over and over again. But it turns out there wasn't a lot of logic. It's simply an if-else.